Hello. Hmm. Hello, can you hear me? Hello, can you hear me? Hello, can you hear me? Hello, hello, can you hear me? Okay, so we will start our third live session. So this is the third week of our course entitled as Physics through Computational Thinking, and the instructor is Professor Aditya Sharma from Azhar Bhopal. And so let us begin our third live session. So in this live session, first I will talk about some technical prelims. So this will include so uh, we will learn about this global variable. Then we will learn how to define a variable to be local, and then we will learn about so if we have some arithmetic expression, then we will learn how to expand them. And suppose we have some expression of this kind, uh, 1 plus x to the power n, then so we can write this expression. So from Mathematica, it is really simple command to write this expression as a constant factor plus x into some multiplication factor plus x square into some multiplication factor, and in this way we can write this up to order of x to the power n. So we so that so if we need some certain multiplication factor corresponding to a certain factor, so suppose we need the multiplication factor of x to the power 5. So from here we can easily get the multiplication factor corresponding to x to the power 5. So how we can get that, and so we can work with that. So that we will go through. Then we will go through random numbers, some properties of random numbers. So how to specify a random number, how to create a matrix out of this random number, and how we can plot this matrix, or we can visualize this matrix from this random number, that we will go through. Then we will go through some certain types of plot like log plot. So when we generally write the plot command, so we in both the axis in general settles to be linear. So if we don't specify anything, this axis and this axis both will be linear. So we can convert any one of them to log or convert both of them to log. So if we convert, so if we have this type of graph where this axis is said to be linear and this axis is said to be log, then this is a semi-log plot. And if you have a plot where both the axes are in log scale, so this is in log scale and this is in log scale, then it is a log plot. That simply means both the axes they are in both the axes are in logarithmic scale. So this we will go through. Then we will learn about some basic 3D plots, how to visualize a 3D plot. What is a 3D plot, that we will go through. Then this parametric 3D plot. Then so this kind of thing, and after that we will learn about this how to work with some data. So if we so whenever we are doing experiment or all this, so we have certain data sets. So suppose we have a data set where this axis is, so we have a data set of amplitude with time. So what in this data set, for different time we have different amplitude. Suppose for 0.01 second we have a certain amplitude. So suppose 2. For 0.03 second we have amplitude 5. 0.06 second we have amplitude of 7 maybe. So this is, so this is what we have a data set. We have one variable, and for that variable we have certain data of another variable. So this is our time data set, and for each time we have this data of amplitude. So how to how to calculate whenever we are doing experiment, so we do measurements repeatedly. So that means whenever we are taking for this time for 0.01 second, we will have few number of data. Like for 0.1 second we have amplitude data to be 2, 2.1, 2.02, 1.97, 1.95, and all this kind of. So for every time we will have this kind of data sets. So these data sets are coming from repeated measurement. So we are measuring certain value. Here for amplitude we are measuring amplitude in number more than one number of times. So we are repeating the experiment for 5 times, 10 times, and for each repetitive measurement we have certain data. So this data set will so for 0.01 second this data set will have a mean value. So suppose so for this data set it is around to be point so 2. So the data set will have a mean value around this, and it will have a spread. So if we get, so because we are not getting the same number every time, we are getting slightly different numbers. So that is why it will have a certain mean value, and around this mean value it will have certain amount of spread. So how to so if we have a data set, then how to calculate the mean, how to calculate the standard deviation, and all this, that we will go through. And after that so we will discuss some basic things about curve fitting. So let us proceed. So before proceeding with this global variable, so let us define two variables. So suppose we have a value p 3 and another variable q to be 5. Then if we perform this operation p plus q square root, then we will have a certain number. So p is assigned to 3 and q is assigned to 5. then p plus q squared, it will be 8 squared and 64. Now suppose we want to replace a value of p to a certain another value. So for replacing, we generally write this command. So this is our expression which you want to evaluate. And previously p is assigned to 3 and q is assigned to 5. Now if we assign another value to p, suppose we assign the value 5, then it should give us then p plus q will be 5 plus 5, and it should give us 10 square, that means 100. So if we execute this, but that doesn't give us 100. So that is because these variables are global. So what does this global variable means? So whenever we are assigning a value to a variable, so here we are assigning the value 3 to p, then this value of the p will, whenever in the next time whenever we are working with p, that will automatically take the value of 3. So that is why the p variable is global now. So we can work with p anytime, and that p will take value 3. So that is why if we replace the value of p with 5 here, it doesn't work. So how to replace the variable? So we one way is that we can assign the new value. So if we assign the value 5, then p will have value 5, and if we now compute p plus q squared, then it will give us 100. So this is one way, and another way we can do that. So that is through this block command. So in this block command, so if we first we are defining the value of p. So since p is now global, so p has the value of 5. But in the block command, if we assign p value to a certain another value, so here we are assigning p value to be 7. So if we do that, it will execute this p. So in this, within this block command, this p is not global anymore. So we can if if we don't specify its value, it will take its previous value. But if we specify a certain different value, it will take that different value and it will execute the expression. So if we perform this, then it will give us 7 plus 5. Say 7 plus this q value is 5, then 7 plus 5 is 12. That means it should give us 144. So it will give us. So in that way, we can clear the we can change the global value to for a specific hello. Hello. Can you hear me? Hello. 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 Where do you have confusion? Can you please specify? So the idea is that like whenever we are assigning, so this p q, these are variables, right? So here we are assigning these values to the variable. So this we are writing 3 p equal to 3. That means after writing this, whenever I am working with p, this p will automatically take the value 3. So that is why it is global, because after after assigning this value, so whenever in the next time, whenever we are calling this p is not a variable anymore. So this is like a normal number. So whenever we work with any numbers like 1 2 3 4, so these are numbers, right? So these have certain specific values. So this is so but our general notion is that whenever we are working with this A, B, C, or all these alphabetic letters, so they don't have any this specific values. So whenever we are writing this type of command, so here p equal to 3, that means now you can forget about p, like p is not a variable anymore. So this this Mathematica will treat p as a number. So it will not treat p as p. It will treat p as 3. So that is why whenever in the next time, whenever we are assigning this p value, so here we are writing this p plus q. So this p, so Mathematica is not seeing this as p, but rather it is seeing this as this number. So it will see this 3 plus 5, and it will execute 3 plus 5 square. So 8 squared, that means 64. So, so how can we change the number once it is assigned? So unless if we don't change it, it will be always take this value. So it turns out that one thing we can do is replace command, but as the variable is assigned here, so by this replace command you cannot replace this value of p. So here Mathematica will not see p as 5, rather it will see as this. So that is why it is still executing this to be 64. But again, if we write down this command, that means now the p value of p is now changed, and it will now treat its value to be 5. So that is why if we again execute this, it will give us the value of 100. So how can we change? So this is one way of changing the value. So here if we do it, it will now be global. So after that, whenever we are assigning this where p value, so this is 5. So suppose when we were working, so in any intermediate state, we want to check with different number. So how can we do that? We can do that with the help of block command. So this in the block command, if we change the value of p to a different value, it will treat it as a local variable. That means within this block, the value of p is 7. And if we get out of this block, it will take its previous value. So that is why whenever we are writing this here, as we are writing this p, it is taking its previous value. The value of p in this block command, it is not storing its value. So the value of p is 7, is solely between in this block, not here. So it will erase this its memory. So here the p value is 7, and it will execute this. And after this execution, if we again want to see its value, then it will show its global value, and its global value is 5. We have assigned here, so that is why it is showing still 5. Hello. Okay, so this is the idea of this global variable and a local variable. So whenever we are assigning a value, it will be global, and if we want to use it as a local variable with a different value, then we can use this block command. So we can always clear the value. So we can write this command clear. So if we write this, then the value of p is now cleared, and now p doesn't have any specific value. So if we write p here and shift enter, then it is not showing its previous value. So by this clear command, we can clear the value assigned to any variable, and so this is the use of this clear variable. So by this clear variable, we can clear any values assigned to any variable. So now next we will learn about expand. So suppose we have any a expression. So suppose, we have this expression p plus q squared. Then we know that this is a standard. If we want to simplify this, it will give us p squared plus 2pq plus q squared. Now, if we calculate this, if we write down this p plus q cube, then we know it turns out to be p cube plus 3p squared q plus 3pq squared plus qq. So in Mathematica, we can expand this any arithmetic expression up to any order. So if we want, we can expand this expression even for n equal to 100, n equal to 1000, and all this. So let us try. So we have to write this command expand p plus q. So let us first clear this q value, because q is assigned to be 5. So clear q. So this p and q, now they don't have any specific value. So if we expand this, it will give us p square plus, so what we know already. Now we can go on the following way, and we can evaluate another other expression, other complicated, any complicated expression that we can get. So suppose 6. So this is the how we can expand this in this way. We can expand any expression. So let us uh, try with another function. So 1 plus q plus 3 p squared and to the power q. So we can do that. So basically we can do any complex kind of we can take any kind of complex arithmetic expression and we can expand them. So this is the basic idea of this expand function. Now we will talk about this collect function. So what does this collect mean? So whenever we are expanding any function, then for so suppose this 1 plus x to the power n. So if we uh, we we can collect its term up to a order of x. So this will have x to the power 0, and after that it the x to the power 1, and it will have some multiplicative factor, and then it will have x squared and some multiplicative factor x to the power. In this way it will go up to x to the power n with a multiplicative factor. So uh, we can express any expression in the following way. So let us see how we can do it. So let us evaluate any a complicated expression. Yeah. So here, so like here, you can see. So this term 1 plus 3a plus 3a square plus a cube, this has x to the power 0, and this term it has x to the power 1 factor, and after that this has x squared into this multiplicative factor, and then x cube into this multiplicative factor. So we for simplicity we can assign a certain value to a. So let us take a value to be 3 and evaluate this expression. So now here this a will be 3, and if we evaluate this and collect orders of this x, then we will get the following. So this is our x to the power 0 multiplicative factor, and this is the multiplicative factor of x to the power 1. This is the multiplicative factor of x squared, and this is x cube. So in this way, we can work. So if there may be cases where we have a complex expression, and we want to know the certain multiplicative factor for a certain power. So suppose here we have uh, this 8, and we want to know what is the multiplicative factor corresponding to x to the power 4, then we can easily get that. So here we can see that the x to the power 4 has this multiplicative factor. So in that way we can work with the any multiplicative factor of any order of x for any complex kind of arithmetic expression. So this is the general idea of this collect. So now we will learn about how to define a function in mathematics. So what does a function means? So suppose we have y equal to sine x. So what does this mean? So this means that this y, this is a function of x. So if we have a certain range of x, suppose x has value from 1 to 10 in steps of 1. So, that means x has value 0, 1, 2, 3. In this way, it has value up to 10. So it can be in integer steps. It can be in more small steps like 0.2, 0.4, and all this 0.6 up to 9.6, 9.8, 10. So x, so suppose we have this discrete value set for x, and for every x we can calculate the value of y. So if x is 0, then we can calculate value of y. So sine 0, it will be 0. And in this way, if we have this value of 1, we can put it and we will get a value of y. So that basically means x is x here is our independent variable, and for every value of x we are getting a value of y. So this is the idea of function. That means y value is not independent, but it depends on x, on value of x. So how it depends? This depends from through the sinusoidal function. So suppose we have this form. So that means y depends on x by this cubic factor. So if x has value 7, then y will have value 7 cube. And x has, suppose we have value 3, x value, then y will have value to be 27. So this is the general idea of any function. That means this y is dependent on x. So how to write any if any function in mathematical? So we can do that in the following way. So we have this, suppose x. So this is the general notion of writing any function in mathematical. Suppose x cube. So this is our function. That means so if we type the following command f4, then we will get 64. So what does that mean? That means this function has the form of x cube. So if we type this f4, then this x value, it will take this value 4 and it will execute this 4 cube. Now uh, try with a different value f of 2. So this will give us 8. Now let us define another function. So let us change its form. So suppose we have a complicated expression, exponential minus x squared plus 2 into sin x. So suppose this is the functional form. If we execute this, so this is the expression. This is what we are getting, e to the power minus x squared plus 2 sin x. This is the functional form. And if we calculate any value, we can calculate any value now. So function of 2. So this will, what this will do, it will take this x value to be 2 and it will execute this expression. So let us see. Yeah. So and this, if we want to get its numerical value, so we have to write down the following command. Yeah. So it will we 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 can get the value of this expression at x equal to 2. So we can get for any range of x values. So we can get from, so we can take the range from of x from 1 to 100, and for that we can evaluate this function, this expression at each point, and we will have an array for that corresponding of x. So in that way we can evaluate a function. Now we can also specify, so this function, this has one independent variable. Now we can construct functions with two variables also. So let us see an example. So suppose we have a function of two variables. So it can be of any form. So x squared plus yx plus x to the power y or something. So let us denote this by z. So now this z is a dependent variable and it depends on two values. Unlike the previous case, in previous case we have one independent variable, and for that independent variable we are getting the expression of this functional form. Now here we have two independent variables. So for this z, it will depend on two parameters, this x and y. So uh, we can calculate any function of we can construct any function of any number of dependent variables. So let us construct a function of two dependent variables. So we have to write down this in the following way. So this is the function, and let us complicate it. So we have x squared plus x multiplied with y. So this is the functional form, and we want to calculate any expression. So suppose we want to calculate this functional form for these two specific values. So what it will do? It will pass the x to assign this value to x. So x will take this value, and y it will take this value, and it will execute the expression. So if we do that, we will get the following. So in this way we can work with any other numbers also. So let us write this as 4 6 4 5 or something. So if we execute this, we will get the the value of this expression for these two numbers. So x will take this value 4, and y will take this value 6, and it will evaluate this expression. So in that way we can write a function which depend on two variables. So in the function form we have two independent variables. Now we can create a function of another function. So what does a function of another function means? So suppose we have a function f of x, this is x square, and we have another function g of t. So suppose this is 1 plus t. Now if we evaluate this expression, so what does this mean? So this means here the g, the function has this form, and for this t value it will evaluate this expression. Now in place of t we are writing another function. So what does this f of x what is the functional form of this f of x? So f of x is x square, so equal it will be equal to x squared. So if we want to write down this expression, so here we have t, and we are writing this as t here. Now as we have here x squared now, so we will get this 1 plus x squared. So in the similar manner, if you want to execute this expression, so what we will get? So we want to now calculate f of g of x. So what does this g of x? So g of t is 1 plus t. So g of x will be 1 plus x. And if we write down this, so g of x is 1 plus x, and f of x, so this has x squared, so f of this it will be 1 plus x squared. Because we can define this 1 plus x as another variable u, so f of 1 plus x, we can write down this as f of u, and this f of u it will simply be u squared. So u is 1 plus x, so it will be 1 plus x squared. So we can see that in general this order of this function matters, because g of f of x in general this is not equal to f of g of x. And we can see that from the expression it has 1 plus x square, g of f of x, but f of g of x, this is 1 plus 2x plus x square. So these are in general not equal. So there may be some certain cases where this functional form will be equal, but they are in general they are not equal. That means their order matters. So which function we are evaluating first, that matters. And so if we evaluate this function, this f of x at first, uh, the expression we get, and if we evaluate g function at first, then the expression we get, both the expression in general will be different. So how can we evaluate this kind of expression in Mathematica? So let us see an example. So let us see the example which we with which we are explaining. So this g of x. So so this is 1 plus x, and we have another function. We have two function here. X should be x squared. So we have these two function. Now let us evaluate this g of f of t. So we are defining another parameter t. So if we evaluate this, we will get the following expression. So let us so g of f of t, which we get 1 plus x squared. Now let us compute this f of g of x. So we have to write down the following command f, and here we will have to g of t. So if we do that, we will get the following expression. So that so in this way we can calculate a function of uh, the expression of a function, and the uh, dependent variable of and the independent variable of the function that we are getting from another function. So we can compute function of a different function, and so on. This is the general idea of how we can use function in Mathematica. So there will be complex examples, so and so more. So we will go through this in the next following tutorial video. So up to now, so this is the basic idea that how we can write any function, and how we can increase the number of parameters, the independent variables of a function, and how to calculate a function that is dependent of another function, and all this. So this type of expression, this we can this will be helpful when we are dealing with loop and all this. So we will go through this again in the in our next tutorial videos. So up to now, so this is the basic idea of how we can use a function. So let us now work with have some basic idea about a random variable. So so we know that what is a random variable. So a random variable basically means, so suppose we are having some we are so suppose we are measuring amplitude, or so suppose we are measuring amplitude. Now this amplitude, so generally whenever we are measuring any value, so suppose then so whenever we are doing experiment or something, then it will have certain correlation. What does this correlation means? So if we so suppose we are throwing a ball, and after a certain time, suppose after 2 seconds, we are we are measuring how much horizontal distance it has covered. So whenever we are doing experiment, we will do this experiment a finite number of time. So we will throw this ball for certain times. So suppose 5 times or 7 times, or like ideally we should do this for very large number of time. So suppose we are doing this experiment repeatedly for 6 times, and we are measuring the horizontal distance it has covered after a certain time. So here this is 2 seconds for. So we will get a certain number here. So suppose the distance it has covered is 10 meter. So here we are getting 10.1 meter, and here we are getting suppose 9.95, 9.97, 10.05, 10.13. So suppose we are getting these numbers. So if we look carefully at this number, then we will see that it is not something which is very random. So it may happen that we are getting here the expression 10. Here we are getting the distance to be 100 meter. Here suppose we are getting the distance to be 0.001 meter, and here we are getting 10 to the power 5. So and suppose here we are getting minus 10 to the power 3 meter. Minus means so since that what is this minus signify? So the displacement is in opposite direction. And suppose here we are getting minus 0.1 meter. So if we look these two data sets, so this is one data set and this is another data set. Now if we look at both the data set, we can clearly say that this it has some correlation. What does this correlation mean? So if we repeatedly measuring the same variable for certain repetitive measurement, then we can see that it have a certain mean value, and around the mean value it has some finite amount of spread. So suppose the mean value is 10, then sometime we are getting this value, sometime we are getting this value. So if we draw the probability, so the value will have a finite spread. Now but in this case, if in this case, if we repeated the experiment for a very large number of time, and if we calculate its mean and variance, then it may turn out that mean is equal to 0. So it has the probability of going in the positive direction, of going in the negative direction, and it can take any values. So that is why its mean will be around 0, and it will have a very large amount of spread. So here the spread is very less, around 10 we have. So if this is 9.9 and this is 10.2 suppose, so we will get if whenever we are measuring, we will get a value in this region. But here we don't know, because if this is truly random, so it can take 10 to the power 5, or it can take minus 10 to the power 5, or anything in between. So that is why here we have this flat kind of data. But here we have a finite spread. So this is a random number. So what? So random number means which doesn't have any correlation. So if we perform the same experiment a number of times, for every time we will get numbers which are totally uncorrelated. So from one value we cannot infer what will be the next value. We don't know. Well, actually we don't know, we don't have any precision or prediction. It can be any value. So this is the idea of this random number. So in Mathematica, if we write down this command random real, so if we don't specify anything in between, then it will create a random number between -1 to 1. So for one run it is generating this number. Now again if we execute this, it will give us a different number. So if we execute again, so we will get another number. So this is, if we don't write anything here, then it will create a random number between -1 to 1. Now suppose we want to create a random number for higher range, then what we will do? Then we have to write down this following command. So random real minus, so this real means it will generate a real value always. It will not generate any complex value. And here we are specifying the range from -2 to 2. So from -2 and 2, it will take any random number. So if we execute this, we will get this, and for repeated execution we will get different numbers. Now suppose we want to generate random number more than one. So this one, if we write down here one, so it will generate one number in this range. Now if we want to generate more numbers in this range, then we have to specify the number here. So suppose we are specifying 10, then what it will do, this command, it will generate 10 numbers in this range. In from -2 to 2, it will create 10 numbers. So let us see. So you can see here that it is creating 10 numbers in this range. Now if we want to control the amount of precision, so what does this precision mean? So here after decimal point, it it is generally giving us 5 digits. So suppose we want to work with 1 digit or digit, then we have to write down this command, this working precision. So if we write down this, then if we specify 2 here, then it will generate random numbers in this interval up to 2 digit precision. So let us execute. So you can see that here this the significant figure of this is 2. So all these numbers, all these random numbers, they have a significant figure of 2. Now suppose we want to increase this, and we want to up we want accuracy up to digit 10. Then we have to write down the following command, and in that way we can generate a random number in this limit up to significant figures 10. Now, can we create a matrix out of this random number? So it turns out that we can. So for this, we have to write down this command. So here we have to write this 4 3. If we write down this, let us first execute, and uh, I will explain. Yeah. So this way, so if we specify two numbers here, so it will create a matrix. So what does this 4 signify? It signifies the number of rows. So you can see here, so this matrix, it has 4 rows. So this is first row, this is second, this is third, and this is fourth, and this 3 means it has 3 columns. So if we look here, so this is our first column, this is our second column, and this is our third column. So in that way we can create a matrix out of a random number. So in this matrix, each element we are taking from this interval. So we can change this interval. So suppose we want to create a random number in between -10 to 10, then we will have to execute this, and we want to create a diagonal matrix, suppose, then we can do this in the following way. Yeah, so this is a matrix of a random number which has 5 number of rows, 5 number of column, and each element of the matrix that is coming from this range -20 to 10, and it is a random number. So that is why each time it is generating something completely different. So can we visualize this random, this matrix? So for visualization, we have to one thing we can do this array plot. So let me first write down the command. So suppose we want from -10 to 10, and this is 5 to 5. So in this way, we can visualize this array plot. So so here we can see that this color, this each color represent to a different number. So this if we this gray, this black, white, and grayish, all this shading, they corresponding to different number. So if we want to create array of more, so suppose we want to have a matrix of 30 row and 30 column. So if we do that, then we can see that here we will have this 30 row and 30 column, and each of these pixel, so these are pixels, and each pixel have different color, because this color represent to this number. So the higher the number, the number which is highest, for that we have this black color, and the number which is lowest, for that we have this pure white. And in for in between numbers, we have in between colors like this gray, uh, black, gray, and all this. So in this way we can visualize a matrix out created out of random number from this array plot command. We will continue after 5 minutes, so we will take a 5 minute break. Okay, so let us continue. Uh, Now we'll learn about this different type of plot. So up to now, whenever we are doing any plot, so we are doing this in linear axis. So this means, so whenever we are plotting, so suppose we have, so suppose we are plotting this y equal to sine x. So this is our x-axis and this is our y-axis, and it will, so suppose sine x plus a constant phase factor. So it will have graph of this kind. So here this x-axis is linear and y-axis is linear. So what does this linear means? Linear means this every data set. So suppose this is our first data set, this is our second point, third point, fourth. So these are points of x for which we are evaluating this value of y. So this, in this plot, this difference, they are uniformly spaced. That means if this is point 1, then it will also be point 1 and it will also be point 1. So similarly in the y-axis also. So these differences, they are uniform. Now for log plot, what we will have, so suppose our this x-axis is linear and this y-axis, this is in logarithmic scale. So that means, so suppose we have this numbers. So if this is 1, then it will be 10 and it will be 100. So when this linear scale and log scale, so when we will use which one? So in which case this log scale is appropriate. So log scale is appropriate whenever we are dealing with this axis which has large amount of deviation. So that means, so suppose we are observing the frequency spectrum of a harmonic oscillator. So what does this mean? So if we convert this in frequency domain, so for a certain frequency, suppose this is frequency and this is the Fourier transformed amplitude. So in this amplitude, so for the resonant frequency, so suppose we are driving the our harmonic oscillator, and around the resonant frequency it has large amplitude, and around, and after that its amplitude will be around close to zero. But in real life scenario, so there are some noise present, and due to that it will have some value of num so suppose this noise level, this is, this has amplitude in the order of 10 to the power minus 6, and this peak amplitude, this has order of 10 to the power minus 2. Now if we want to visualize this, now if we want to visualize both this noise level and this peak amplitude level in the same graph, then if we do the, if we keep our y scale linear, then in that case compared 10 to the power 6 is very small compared to 10 to the power minus 2. So if we look this in logs, in linear scale, so it will get, we will get a peak here, and here we will get 0, because it is 10 to the power fourth order of lower value. But if we so if this is 10 to the power minus 2, then it will be zero point 0.9 into 10 to the power minus 2, it will be zero point 0.8 into 10 to the power minus 2, and in that way it will go up to, so here we have zero point 0.1 into 10 to the power minus 2, and this will be 0. Now in the logs, if we do the same plot in the log scale, then in this axis, so if this is 10 to the power minus 2, then it will be 10 to the power minus 3. So why that is the case? Because we know in logarithmic scale, so suppose we have this x to the power n expression. So this powers, for if we take the log of this, so this power will come as a multiplicative factor. So it is n log x. So that is why if we have log of 10 to the power minus 2, so it will give us minus 2 into log 10. And if we have log of 10 to the power minus 6, it will give us minus 6 into 10 to the power log 10. So in the logarithmic scale, this this is 3 orders of magnitude higher, but in linear scale, this is 10 to the power 4. So that is why in the log scale, we can observe both the effect of this peak amplitude and also of this noise floor. So 10 to the power minus 6 and this is 10 to the power minus 6. So we will get this kind of plot. So in the linear scale, we cannot observe the effect of this noise floor. But if we look this and look the same data, but if we make our y-axis in logarithmic scale, then we can observe both the effect. So that is why when the that is the case when this log plot is very useful. So if we have two different curves which has very large amount of or which is order of magnitude higher, like 10 to the power 5, 10 to the power 6. So, and if we want to visualize both of them in the same scale, in the same graph, then we have to uh, we have to use this logarithmic scale. So, let us see some example here. So, suppose we are plotting this function x to the power x, and x is the range of x is from 1 to 5. So, if we plot this, we will get this kind of expression. Now, if we plot this in and now if so you can see that this is evenly spaced, these numbers 200, 400, 600, 800. Now if we plot the same thing on the log scale, then we will observe this. So you can see that this is 10, this is 100, this is 1000. So that is why here it is increasing as exponentially, but in the log scale it is increasing as uh, almost linear or quadratic kind of thing. So we can plot different expression in the same graph. So let us do. So here we have three expression. One is x to the power x, another one is exponential of x, and this is x factorial. So if we plot this in linear scale, then we will have this kind of expression, this kind of plot. But if we plot this in log scale, then we will get this. So this is the visual difference. So visually it will seem to be different, but we have same data set. What we have done here, we have changed the y-axis in logarithmic scale. So that is why they it may seem that they are different, but basically we have same data set, but we are only changing the y scale to log. Now look at other examples also. So if we do that. So in that case, if we observe that this x to the power 5, it is so higher that we cannot see the effect of x to the power 4. How does this x to the power 4 function, 3 function or 2 function changes with x? So in the in the linear scale, we cannot observe how they are changing. But now if we change this in log scale, then we can see that how they are changing. So this is that is why when that is the case when the log scale will be useful. Now we can convert this x-axis also in the logarithm scale. So for that we have to write down this command log plot. So if we write down only log plot, then it will keep our x-axis in linear and y-axis in logarithmic scale. But if we write down this command log plot, then it will convert both the in logarithm scale. So if we execute this, then we can see. So this is also logarithmic scale, as you can notice, and this is also logarithmic scale. So this is the basic difference between this linear plot and semi log plot and log plot. So now let us learn about this 3D plots. So suppose we have a variable. Uh, Suppose we have this kind of expression: sine x square plus sine y. So let us turn this to z. So here, this z, it depends on both these variable, on y and x. So suppose we have a range of x from 0 to 10. So suppose this is x range our. So this is 0 and this is 10. And so here this x and y both are independent variable. That means x and y, they don't depend on each other, and that is why we cannot write down x as a function of y. So y has is so suppose y is also from range 0 to 10. So this is y range, and so it will look like an rectangle, and in between this rectangle, for each x and y data point, we will get a value of z. So, so suppose for this point we have so suppose this is x equal to 3, y equal to 4. So suppose this is a point, and for this point we will get an value of z. For in this way, for every point in this rectangle, we can evaluate the value of z here. So how how can we see what is the value of z in the plot? So we can do this by doing a 3D plot. So what does this 3D plot mean? So it will so in this two axis, this is our two independent variable, and if we consider another axis that is out of the plane of this of this screen. So, suppose this is z axis. So this is perpendicular to both x and y, and in this axis we can show its value. But so suppose for this point we have z value of this, and for another point we will have z value, we will have different z value. So uh, and by specifying the we can do this by color plot. So in this range, for every pixel we will get a different color, and each color corresponds to a certain number. So two different colors means we have two different number at these two different region. So suppose here this is blue, and suppose here this is green. So I will show that this in example. So let us first learn how we can analyze the plot. So here suppose this is green. So that means in this point, what is the value of z, and in this region the value of z, this is different. So how can we do this 3D plot? So let us do this in mathematical. So this is the expression. So we can write down this as z equal to sine x plus y squared. So this is our expression, and for a specific range of x and y, we want to see how the z changes. So we can, if so for that we have to write down this command plot 3D. So this means it will create a 3D plot, and in the so let us first evaluate this. Yeah. So here you can see. So this is our x-axis, this one. So x is from -3 to 3. So here we this x-axis is from -3 to 3, and this is our y-axis. So this is from -2 to 2. and for each point we will get a value of z. So the height of this cur- curvature that indicates the value of this what is the value of this expression, this sine x plus y squared. So is it clear to everybody? Okay, so we can do this for different functions. So let us evaluate this same for another function. So what is happening here? So here we have two different curves. So this is so we have one curve which is z equal to x square plus y square, and we have another curve which is z equal to minus x square plus y square, and we are plotting this two plot in the same graph. So as you can see here, so this upper curvature, this correspond to this x square plus y square, and this lower one, it corresponds to this z equal to minus x square minus y square, and the limit is of this x scale and y scale. This is from minus 50 to 50, and we can change this. So we can do this from suppose 20. So now you can see that the axis limit has been changed, and this color function, so basically this implies what is the color that we want to use in our graph. So we can erase this also. So if we execute this, then you can see that it will for both the expression, we have different color combination, and the height of this curvature from this center point, it basically signifies the amplitude. The more the height is, the more the amplitude of the function at that point. So this is how we can plot any 3D we can visualize any 3D function in Mathematica. So we can also do a parametric plot also. So let us first uh, discuss what is a parametric plot. So suppose we have two variable x and y, and suppose they depend as this way. They depend on a third variable. So how we can visualize this? So suppose we have this expression x squared plus y squared equal to 1. So suppose we have this mathematical expression. So so if we replace here x equal to sine t and y equal to cosine t, then for any value of t, this expression will always give us 1. So if we execute this x squared plus y squared, then we will get sine squared t plus cosine squared t. So this will be 1. So whatever be the value of t is, it will always be 1. So we so in parametric plot, what we do, so in parametric plot, we see how x changes with time and y changes with time, and we plot this x versus y graph as a function of time. So for t equal to ti, we will have certain x value xi, and y will have certain y value. So this xi is sin ti and yi will be cosine of ti. And for another time, suppose t equal to tf, t equal to tf, we will have different x value. So x, suppose a we have x equal to xf. So it will be sin tf, and yf, it will be cosine of tf. So for every time, for each time step, we will have different value of x and y. So in the plot, so this x and y, they are not dependent on each other directly, but they depend on each other through this through a third parameter. So this in this case, t is the independent parameter, and depending on the value of t, both the x value and y value get updated, and with t we can see how the uh, we can see in graph how this x and y value changes. So this is a 2D parametric plot. So that we have discussed earlier. So what is a 3D parametric plot? So 3D parametric plot, it is nothing but we have another extra variable. So suppose we have this kind of expression, x equal to sine t, y equal to cosine of t, and suppose we have another variable z. So that depends on t, suppose as t. So if we want to plot both all the x, y, and z axis in the same graph, so this will x and y, and out of plane we have our z direction, and we want to see with time how this x, y, z value changes. So for that we have to do the parametric plot. So as you can see here that this x and y, if we, how it will change, this x square plus y square is 1. So in the xy plane it will create a circular kind of trajectory for all the time, but the z axis, this is also changing with time. So it ultimately it will create a spiral. So it will be of this kind. So let us visualize this in mathematical. So suppose we have this expression, so cosine of u, and suppose here we have sine of u. So let us first plot this. So this is the parametric plot. So if we have x equal to cosine of u, y equal to this sine of u plus cosine of v, and z equal to sine of v, then for this range of u and v, we will get this kind of parametric plot. So let us look at another example. So that is the example that we are talking about. This uh, x equal to sine of t, y equal to cosine of t, and z equal to u. So suppose for first let us just consider this as u, and if we plot this for u value from 0 to 20, then we will have this kind of spiral. Now what we can do, we can divide this by a number, and we can manipulate the value of a. So we have learned about the manipulate command. So for manipulation, so this is our manipulate command. So what does this mean? This means basically we want to manipulate the plot that we are getting here for different values of a. So let us execute first. So this is we are getting for a value 1. So if we change the value of a, then we can see that the how the spiral changes. So the idea is that if we divide by a larger number, then the distance it is traveling in the z direction with time, that is lower, and that but if we divide this with a smaller number, then the distance in the z direction travel in unit time step, it will be larger, and that is why for smaller value of a, for smaller value of a, we the length of the spiral in the z direction, it is very large. So, is there any question? And so for every kind of plot that we have plotted earlier, we can plot different parametric plots in the same graph. So like we have plot previously different graphs. Like just suppose in case of 1D, we have plot y equal to sine of x, y equal to exponential of x. These graphs we have plotted in the same graph earlier. So here also we can plot two different parametric plots. So this is one parametric plot, and suppose we have another expression for another parametric like this: sine of t squared y equal to 2 into cosine of t, and z equal to t square. So these two parametric plot also that we can plot in the same graph. So for that we have to write down this following command. So if we so this is our one parametric plot. So this is one axis, this is the second axis, this is third axis. So this curly bracket, it within this curly bracket, this is our one parametric plot expression, and after that in another curly bracket we are putting our second expression here also. So these two plot we want to plot in the same graph, and after that we have to specify the limit of this u and v. So these are our independent functions. So we have specified the limit here, and if we execute this, then we will get this kind of parametric plot. So you can play around with it. You can change expression. You can even write down different expression, and you can visualize how they will look like in this parametric plot region. So you can also change color of this plot. So suppose you want to do it green. So if you want to do it green, just you have to type the color of the plot. Then you will get this kind of plots. Now. So these are some basic things about different kinds of plotting, and since we have discussed about this random numbers, how to define a function, and how to work with this arithmetic expression, how to simplify them. So now we will learn about how basic about this data analysis and thing. So whenever as I have mentioned earlier in the talk, so this whenever we have any kind of data set, so whenever we are doing experiments, so basically we took the same data of a different uh, ensemble. So suppose like we are calculating amplitude of a certain thing at a certain time. So what we will do, we take the measurement repeated time. So suppose we are measuring its amplitude for t equal to 1 second. So we will measure for we so basically we will suppose 100 times measuring this, and after that we will take its mean, and it will have some kind of standard deviation around its mean value. So how we can compute this mean and standard deviation and all this in Mathematica? How we can deal with this data in Mathematica? So suppose we have this data. So we suppose we are now working with the fictitious data. So suppose we have y equal to sine of omega t. We have this expression. So this is the expression of a simple harmonic oscillator. So with time, its amplitude will change in this way. So if we look this in plot, it will have this kind of expression. So this is t and this is y. So suppose we want to measure its amplitude for time. So suppose we want to measure at time 0 second. So suppose we don't know how this, we have no prior information about this graph. Now we know that y equal to sine of t, it behaves in this way. But suppose we don't know, then what we generally do. So for this, suppose for this time limit, it so for suppose this is our time axis, and for each time we will measure its amplitude. So for time equal to 0, so at initially we will measure its amplitude, but we will not measure its amplitude for one time. We will measure repeatedly. So suppose we are performing the same experiment 100 times. So we will have a range of y values. So at time equal to 0, so suppose we are getting amplitude to be 0, 0.02 minus 0.01, and in this way we are getting 100 values. Similarly, for t equal to 1 second, we will have this kind of data set. For t equal to 1 second, if we repeatedly do the experiment 100 times, we will get 100 values, and so on for every time. So for t equal to 2, we will have a data set. T equal to 3, we will have a data set of y, and so on. For up to 10, we will get a data set. So let us try to implement this in mathematically. So generally we can write this as this. So we have learned about this random number. So suppose we have an expression of this kind, t into omega into 1 plus 0.1 into random number. So in this expression, so if we evaluate the value of y different times, so due to this random number, we will get different values. So if we so how many times we are doing this, so each time we will get different y value, and that is how we can mathematically create a fictitious data out of this curve, this y equal to sine of t. So this is what we already know. But if you want to create a fictitious data, real looking data, then we have to just modify its frequency with a and multiply. We have to add some randomness in the frequency. So that is why. So suppose at a certain for one run we have this 1 plus this expression. Suppose we have to be 1.05, then this omega will be modified by this, and suppose we are for another time the random number generates some value for which we get this expression to be 1.02. So in that case, we will have frequency to be this. So that is how we can create a fictitious data out of this known kind of equation. So let us look at how this behaves in Mathematica. So let me first write down the command and I will explain this. So this is what we are talking about, this omega t plus this is our expression, and so this 5 into omega t, and this round means we are so if we only evaluate this expression, so this 5 into, let us just work with this first. So let me suppress the output, suppress this output also. So if we evaluate this, so suppose we are getting this. Now if we again evaluate this, so we, if we look carefully, this number 3.09533, this changes every time. So every time we are running this, we are getting a different number. So again, yeah. So for each time we are having this different expression. So for even if that value, so if we put t equal to 1, so for every time, so if suppose we are putting t equal to 1 here, so this is the amplitude after 1 second. So suppose this is our first experiment and we get this value. Now if we again measure this, then we are getting this value and again measure. So in that way we can do repetitive measurement fictitiously in Mathematica and we can create a data set. So this is the amplitude at time 1 second. So this is how it will change. So this is the first command, and here we have round. So round means we so let me write down first. So we evaluate this, then this means it will give us 3 digits after this decimal point. So if we want to, so if we want higher accuracy, then we can increase this number, and if we want lower accuracy, then we can decrease this number. So this round command, this is basically for up to how much precision we want to know the value. So and after that we will create a table of this. So table of this for so for different time. So this is, we have here t, and we have to specify the range of t. So suppose this is from 1 to 10, and we so this is our data set for one experiment. So we perform the experiment first time, we get this data set, and suppose we again measure the we again do the experiment and we are getting a different set, and we, if we again do this, we are getting another different set. So we have to accumulate all this data in for every time we are repeatedly measuring this. So for that, this second table column is there. So if we write down here table, so let me do this in table form. Yeah. So this is our first. Uh, in general, it uh, the data corresponding to t equal to initial value, that means for t equal to 1, this is along this column. So this is for t equal to 1, we are doing different experiment. For t equal to 2, this is for t equal to 3, for t equal to 4, and so on, 5 6. So this is our one data set, this is our one data set, and this is our another data set. Now suppose we want to transpose this. So for that we have to write down the following command. We have to write down transpose, and suppose we store the data. So data 1 equal to this, and if we want to visualize this data 1 in table form, then we have to write down this. Yeah. So now this row, this each row corresponding to one experiment. So this is our first experimental observation. This is our second experimental observation, and this is when we are repeatedly measuring the doing the experiment third time. This is fourth time, and this fifth time. So this is how we are getting this data set out of this known function. So now we want to assign the value of time also. So this is row this first row corresponding to initial time. This second row it corresponds to t equal to 2 seconds. This third row corresponding to t equal to 3. So how can we show that in plot? So for that we have to do write down this prepend command. So prepend, and in prepend we have to specify the value of time. So time is basically from 1 to 10. So we will write down this command range. Okay, so this will not be here. So this is our this is kind of messy. So if we want to visualize this in table form, so you can see that this is our time. So for initial time for 1 second, we for these are different experimental observations. For 2 seconds, these are different observation. For 3 seconds, these are different observation. So for every second, for suppose for t equal to 4 seconds, we are measuring this. So it will have a mean and it will have a standard deviation also. So how can we calculate the mean? So we can calculate mean. So for that we have to write down this. So data 1. So what does this command do? So this will do. So we have our data table, and from that this first number, it represents the row. So if we write down here 4, then it will take this fourth row, and if we here we have to specify the range of column from which values we want to consider. So if we write down, so let us first evaluate this, then it will be easier to understand. So 4, and we are basically storing here this 2 to 3 value. So this 2, now if we increase this, suppose 5, then we can see that these numbers are there. Now if we want to take all the observations, then we have to just leave this blank, and if we execute this, then it will give us. So this is our displacement corresponding to t equal to 4. Now if we want to visualize see what is the displacement corresponding to t equal to 1, then we have to just write down 1 in place of 4, and if we execute this, then we will have this data. Now suppose we want to see what is the displacement for t equal to 9. So for that we have to just put it 9 here, and you can see that this row, this is here. So this is our displacement for so let us name it. So let us denote this set. So yeah, now set is this one. Now if we want to calculate mean of this, then how we will do that? We have to write down just this command, mean of set. So this will be the mean, and how we can calculate its standard deviation. So standard deviation we can write down this by following command. So this is the general formula of standard deviation. Uh, you can go through any standard textbook, and you will get how to what is the formula for standard deviation, and to calculate the standard deviation of any data set in mathematics, you have to write down just this command, and if we execute this, then this is the standard deviation corresponding to t equal to 9 seconds. So for t equal to 9 seconds, we have this mean and this standard deviation. We can calculate this for t equal to 2 seconds. So if we do this, so if we execute this, then this is the mean for t equal to 2, and this is the standard deviation for t equal to 2. Now, if we want to visualize all the mean and standard deviation in a table form, then just we have to write down this following command. So if we execute this, so let us see this in table form. So for that we have to write what is our data which we want to see in table form, and we have to write down table form. So if we evaluate this table, okay, so this f will be capital. If we execute this, then you can see, so this is our initial time. So for initial time, the data that we are taking is, we are getting these values, and these values have mean this, and this is standard deviation. And for each time we can in the from this graph from this table, we can see what is the mean value for each time and what is the standard deviation from this time. So this is regarding this how we can work with any fictitious how we can create any fictitious data. So we basically create this with the help of this random number. So and with the random number, so we basically create a table first. So in this table, each row corresponding to different sets of experimental run that we have done. So this is our first set of observation, this is our second, third, and in this way we, for each observation, we can calculate what is the mean value and what is the standard deviation value of the observation for each time step that we can calculate in the following. So is there any question?
No question from my side, sir.
No. Okay. Okay, so I think this is enough for today. So in the next week, we'll first start about this curve fitting, how we can do curve fitting in Mathematica. So these are very useful technique to for experimentalists to analyze any data set that we get from our experimental setup. So in the next week, we will start with that, and I will share the video link and the link of this method and this mathematical file with you guys, so you will get it, I think, within 1 or 2 days. So this is it for today. Thank you.